All right, hey, Mr. What, how's it going?
Hey, Mr. Z, good to see you here.
Good to see you too. Talking about volcanoes, huh?
Okay.
One more time.
So we have the 3 different types of volcanoes to talk about in this segment, and then some other features of volcanoes, some special features, right?
Yeah, we have some volcanic hazards, and then we're going to talk about plate tectonics and volcanism.
Right.
And then I think that's it then, right?
Okay, so let's start with the first type of volcanoes. We'll start with shield volcanoes. What do we know about shield volcanoes?
Well, one is that it's its shape, right? If we're going to talk about 3 different volcanoes, and this first one is the shield, it's the largest of all the 3. And its shape is really interesting. If you actually took a shield, like a warrior shield, and you kind of turned it upside down, right? That's kind of the shape of the volcano. It has a really, really broad base, right? And then the slope of its flanks or its sides are going to be really, really low angle. Like you wouldn't really need climbing equipment to climb up to the top.
So when I think of a volcano, I think about a nice triangular shape, and that's not what a shield
That's
volcano
not what a shield
is.
one is, and we're going to get to those types of volcanoes coming up soon.
Okay.
And an example of this volcano is Kilauea in Hawaii that we've seen quite a few videos on already.
So I'm thinking about the video that we saw of Kilauea, and we saw lots of very hot, low viscosity magma being erupted and then flowing gently down the slopes. And I think when you have that very runny, low viscosity basaltic magma is when you get those thin veneers of lava that spread out over a very long distance, and that's what's going to form the shield volcano, right?
So not having pyroclastic eruptions, stuff, ash, and pyroclastic material shooting into the air is not what's going on here with a shield volcano.
So when we look at the examples like Iceland or like Hawaii, we're typically finding a basaltic composition for these volcanoes.
So very low silica.
And we're talking about the largest. These shields can be 100 or more miles across. Yeah. And they extend, in the case of Hawaii or Iceland, all the way down to the bottom of the seafloor. So if you were to take that out of the ocean floor and look at it, say, next to a huge mountain, like mountains in the Himalayas, it would rival those huge mountains.
I believe it would be taller than Mount Everest.
These are the largest mountains on the surface of the Earth.
They are.
They're just partly underwater.
Yeah, exactly.
Okay. So that's our first type, our shield volcano. Okay, good. Let's go on to the next type.
Okay. All right, this one of my favorites. All right, this next one is the composite or stratovolcano, and we did see a video clip of this, a real short one, which was Mount St. Helens back in the first segment. And this volcano is a lot different. It doesn't erupt like the shield volcano, does it?
No, it doesn't. Very different eruptive style. So these are very dangerous eruptions typically. So some of the features of a composite or a stratovolcano, the shape of the cone is very different. We're not talking about a broad shield anymore. No. We're talking about a cone shape, a triangular shape.
So a narrower base.
And they may be several kilometers across at the bottom. Now, the top of it, the summit area, is typically much steeper. The slope of it is typically much steeper than further out on the flanks of the composite cones.
Yeah.
And these types of cones form in that shape because of the alternating layers of pyroclastic material and lava flows.
Yeah, so the eruption itself, it starts out with this huge pyroclastic explosion, ash and debris into the air falling back down, and once that's kind of done with, right, then we get lava oozing out of it, right, and kind of coming over its flanks then and its sides. So if we were to look at like a cross-section of a stratovolcano, we would see alternating layers of pyroclastic material and then lava flows on top of it.
Right. And these particular types of volcanoes typically have an intermediate composition or an andesitic composition. They tend to have higher amounts of gas. The lavas that are coming out of them tend to be higher viscosity and lower temperature than those of a shield volcano.
So we have more silica in here, I would assume, which gives us the higher viscosity and then gives us the more explosive eruptions.
Correct. The other thing about these volcanoes, which we're going to talk about in a couple of minutes, is they are very characteristic of convergent plate boundaries. Yeah. Okay, let's go on to the third type then.
Okay. All right, the last one here is the cinder cone, and we also watched a video about this one, Paracutin, and we said we were going to mention or talk more about it when we got here to this segment. All right, so what do we know about these guys?
So Paracutin volcanoes are the smallest, and they are only about 1,000 feet high at the most. They are volcanoes that you're going to be able to see if you're looking out on a landscape. Being a small one, they tend to be very steep-sided. And in a Paracutin type or a Sunset Crater type volcano in Arizona, these cinder cones called cinder cones because they're made up of cinders.
Yeah.
So cinders are like a scoria material,
pyroclastic
material that's going to be erupted from that volcano.
Yeah. So the eruption is going to be violent. It's not going to be like the shield volcano.
But because they're such small structures,
yeah.
it's not as deadly as a violent eruption of a composite cone would be. Right?
Got it. Yeah, definitely.
So another great example of this, and we're going to talk about this little place in a little bit here when we talk about caldera formation, is a place called Wizard Island, which is actually really neat because it's a little cinder cone inside of a bigger crater.
Yeah, that is going to be neat to talk about.
All right, so let's go on to the next slide.
All right, volcanic hazards. All right, so the pyroclastic flows we have talked a lot about. Probably the most dangerous thing associated with the volcano, but not associated with every type of volcano.
Correct.
So we do associate it with the shield volcano, with the, not the shield volcano, with the composite cone and with the cinder. Right, so that's where we're going to get those gases, the ash, and then lava flows. And then with the shield, we're also going to get some lava flows too, but not the pyroclastic material.
And we have a specific type of pyroclastic flow. It's called a nuée ardente.
I've never heard of that before.
I know.
So
it's a French word.
Yeah.
It's a nuée ardente. And what a nuée ardente is it's more dense and it is hot. So this is a cloud of very hot, very dense ash material primarily that actually flows and hugs the sides of the volcano as it flows down the sides of the volcanoes. And because of the heat associated with it, it is very deadly.
Yeah.
So in a situation like the eruption in Vesuvius, where it killed all the people in Herculaneum.
The ash people.
The ash, it's also hot ash. So what it does is not only get into your lungs, but it sears your lungs because of the temperature, high temperature. So that's a nuée ardente. It's a glowing, if you can see a nighttime picture of it, it's a glowing cloud of pyroclastic material flowing down the side of a volcano.
Wow, I never heard of that before.
Yeah. And how about a lahar?
Yeah, lahar, that's an interesting one. That's like a debris flow from... Is the volcano erupting when a lahar forms?
Well, lahars can actually form for many years after the eruption of a volcano. So in the example of Mount Pinatubo in the Philippines, they experienced lahars for about 10 years after the eruption of that volcano. And what happens is the ash that's along the slopes of the volcano is continuously remobilized by large amounts of water. So if you have a big tropical storm go through there and it floods out the area, it's going to pick up any ash laying on the ground, carry it down any channels that are there. And this can actually be almost the thickness, the viscosity of cement that is flowing down a channel. And it is the mixture of volcanic ash and water.
Got it.
So those can be fairly dangerous as well. They're very erosive.
Got it. Oh, that, definitely.
Yeah. All right, so we've talked about shield volcanoes and composite cones and cinder cones and some of the hazards associated with them. Let's talk about some special features of volcanoes. So let's talk about how a caldera can form.
Okay.
And I think this is a really interesting slide because the students have this four-step or four-stage process, and we're using an example here of the Crater Lake or Mount Mazama volcano. Do you want to take them through this?
Yeah, well, let's identify some of the parts here. First, we have the magma chamber, which is identified, right? And it's actually in all of the slides themselves, so we can see that. We can see that the volcano is erupting. So I guess in the first slide, it's just kind of smoldering. And then in the second picture here, we see that the eruption is actually taking place. You can see the pyroclastic material flowing through and then lava flowing out afterwards, right? And this magma chamber is going to begin to empty, right? All that material is going to end up being ejected out into the atmosphere and along the sides of the volcano, and then all of this rock here that's now been fragmented, right, is all going to kind of cave into each other into that void space that the emptied out magma chamber has left behind. As it kind of collapses in on itself, in this last picture here, we actually got a formation of a small cinder cone, and I don't know if you can see me pointing to that, a small cinder cone here that actually created an island inside the water-filled crater.
Okay. So essentially, this is a composite cone.
Okay,
right? It has erupted. The magma chamber has emptied out. The summit area has collapsed because the magma chamber is emptied. And the caldera formed where the smaller crater was.
Yeah.
It just filled up with water through rain and snow
Sure.
over time, right? And the particular crater here, or caldera here, is actually very deep. And that's Crater Lake. And then Wizard Island formed in the middle of it as a little cinder cone.
Yeah.
Very cool.
Yeah, it is cool.
All right, so what other kinds of features are we going to be talking about here in terms of volcanic eruptions?
All right, well, we're going to be talking about flood basalts. Extensive fissure eruptions can be hundreds of miles in length, miles thick, basaltic layers of separate lava flows.
Okay, so some things we know about basalt. It's mafic, it's dark, it's aphanitic, it's low viscosity, it's very hot, it's very fluid.
So what type of volcanoes would that be coming out of?
We're not really dealing with volcanoes as in the
Sure.
cone or even the shield.
Yeah.
Now we're thinking about cracks that open up that could be many, many miles or even hundreds of miles long. A crack opening up in Earth's surface where over a long period of time this basaltic lava just pours out and covers hundreds of square miles or even thousands of square miles of land and covers them up to miles thick. So we've got a great map here
Yeah, it is a great
that
map.
shows some of the flood basalt deposits. And some of the largest and the most well-studied are the Deccan traps, which are in India. And you can see, if you take a look at your map, that a large portion of India is covered by that. And then you can also see in the United States the Columbia Plateau, or the Columbia flood basalts are there. So each one of the continents actually has some flood basalts on it.
Yeah.
So huge outpourings of lava onto the surface in flood basalts. Okay? And another feature is a feature called lava dome. So lava domes are really kind of the opposite of a flood basalt.
Yeah. Well, they're not going to really kind of flow out just like the basaltic lava would. They actually is just like a large piece.
It tends to be andesitic in composition, intermediate in composition. So these are very, very viscous, very low temperature.
So they're not going to kind of flow out.
They aren't going to flow out. They're just going to bulge up. So last year, actually, there was some activity on Mount St. Helens inside the crater, where there was some pressure from underneath of this cool viscous lava that was pressing the surface of the crater upward. It was causing it to bulge upward. And that's called the lava dome. So it never broke through, and you can see a picture of it here on the bottom right corner. It's like a little small volcanic structure inside the crater of Mount St. Helens, but this is actually the lava dome, and you can see some steam arising from that. So there's also one at Long Valley, California, and there's a lot of obsidian that's associated with that particular volcano, and then also in Mono Crater. So that's lava domes. So I think here we're ready to move on and talk a little bit about the plate tectonic association of each of the different types of volcanoes. Can we kind of constrain that a little bit and look and say, you know, on a certain type of plate boundary we're going to expect to find a certain type of volcano?
Yeah, we can. We can take a look at the plates themselves and what's actually going on there, and then hopefully we can kind of see what volcano may be present at what plate boundary.
Okay.
So we've talked about Mount St. Helens, and we briefly mentioned that in the second segment, that there was the Juan de Fuca plate subducting underneath the North American plate, and we know that Mount St. Helens is a composite cone volcano, right? And we know that it is of andesitic lava, so that's kind of intermediate, so which is going to be viscous, right? So let's find Mount St. Helens on this map over here. It's right behind you.
Right here.
All right. So we've got a composite cone volcano there, right? And if we think about what's going on, we have the oceanic plate, the Juan de Fuca plate that's going underneath the continental plate, right? And that plate is being destroyed or causing melting, right? And if we think about what the continental crust is made up of, which a lot of it is silicon and oxygen and more of like an andesitic granitic type crust, right? That's what's being melted to create the lava, and that lava ends up becoming viscous.
Well, you've got a couple things happening. You've got that downgoing basaltic slab. You've got some of the sediment that collected on that ocean floor being dragged down in the subduction zone. So you've got a lot of water there that's going to cause the temperature of melting to decrease. So you can have more melting at a lower temperature of those types of materials, and then because they're less dense, they're going to buoy up towards the surface, and that's how that volcanic activity forms in convergent plate boundaries. But we also have to remember that we've got the ring of fire.
Yeah.
Right? So let's see. You can start over there on the right side of this map and show us where the ring of fire is in the western portion of the Pacific.
Yeah, so if I start here just to the northeast of Australia, I kind of make my way around over here on the east coast of Asia, and then up over that way, almost to Alaska. And I think Miss Awad's going to pick it up over there.
We're going to pick up here with the Aleutians, so you can see all the volcanoes that make up the Aleutians. And then coming down the coast of North America to the Juan de Fuca convergent plate boundary. We transition here into a transform plate boundary.
And we don't see any volcanoes
And we don't, but then we transition back into convergent plate boundary. So all through the Andes, we've got more volcanic activity. So there are a lot of volcanoes there, and I bet you those are composite volcanoes, and they're erupting intermediate or andesitic type materials.
Exactly.
And they would be similar to the other composite volcanoes that we've already talked about.
Exactly.
Okay.
All right.
And if we want to look at things like shield volcanoes, we know we've got Hawaii,
which is a hot spot.
A hot spot, and we have Iceland, which is a hot spot, although it's sitting on top of the divergent plate boundary.
Exactly.
And then if we look for some of the cinder volcanoes, cinder
should we mention what's being melted at the hot spot and then in Iceland?
Yeah.
Because those are different kinds of volcanoes, and we know that they have quiet eruptions and that their lava is not as viscous.
Okay. And then we've got cinder cones, which are kind of sprinkled around. So we have Sunset Crater here in Arizona. We've got the ones in Mexico and various other places. But the big ones to remember for the plate boundary associations, convergent plate boundaries, and composite cones.
Yeah, definitely.
All right, great.
Yeah.
Okay, so that was a lot.
That's, quite a bit.
Plus we've got a mastery check quiz for them, so hop out to the webpage for your class and hop on that quiz and do a great job with that, and we'll see you in class tomorrow.
Yeah, all right. Thank you very much, Miss Awad.
Great. Thanks, Mr. Z.
All right.
Take care.
All right.
Bye.
Bye.